Welcome to another video from Lockdown Electronics with me, Bill, and this time we've got a bit of retro chip recreation. I was recently at my mother's. She's well into her 90s, but she's always very keen to save anything electronic to see if I want it for anything, and she got a couple of old telephones that she didn't want. They were the sort of modernish, probably 90s desktop types, so I thought, yeah, I'll take them and have a look what's in them, and I managed to recover a few components, a couple of decent small speakers, a few bits and pieces like that. And on the circuit boards there was some 8-pin DIL integrated circuits. Now they were relatively easy to remove because they were the conventional DIL sockets, chips, so I took them out and put them to one side and thought I'll just look up what they are, and it turned out they were ringers. So I thought, well, that's interesting, I might just have a look how they work. So that's what today's video is about. It's a bit random in one sense, but it's also a bit nostalgic because these things were everywhere, I would imagine, and in a few years time, once we've got rid of the old telephone system, there'll be no requirement for them anymore. So I guess it's a snapshot of history too. So let's start by having a detailed look at how the old phone system works. I'm going to say work because it still does work in the UK, and how the technology came to deal with having to handle the vagaries of that system. Okay, let's start by just having a look at where this chip is expected to operate. And post office telephones might sound like a strange phrase if you're outside of the UK. If you're not outside the UK and you're old enough to remember it, the post office used to run the telephone service, and the kind of telephones that they used to produce looked something like that. Well, okay, maybe slightly more modern than that, but actually that kind of telephone, which essentially is meant to work on a high impedance analog circuit, would, as far as I understand it, be able to be plugged into my telephone socket here at the moment, and it would work correctly, even though it's pretty old technology. And certainly the telephone we had in our house as when I was a child looked a little bit more modern than that, but essentially it contained the same electrical circuits and components, probably just slightly more modern versions. So to enable those phones to work, there was some quite interesting technology, and in the UK it was the post office who ran the telephone system. It's since been long privatised, but before that it was the post office, and they had a very accomplished technical department. In fact, the Post Office Research Centre at Dollis Hill was very famous indeed. Here's a photograph I took last year. This is the replica of the Colossus computer, which you can now see at the National Museum of Computing down in Bletchley. It's next to the Bletchley Park site. Definitely worth a visit. Fascinating to see it. And it was the post office engineer called Tommy Flowers who actually created and built the first and subsequent Colossus machines, which enabled the Allies to speed up their breaking of the Lorentz cipher. And so that's essentially the world's first proper digital computer, and sadly it got broken up after the war, and so history is history. But although the post office might sound like a very old-fashioned name for something to run a telephone system, they were actually extremely good at what they did, and certainly Colossus was a very impressive piece of kit. So let's look at what that telephone on the left there was actually connected to. And under normal circumstances the circuit would look like this. The telephone line itself is 2 wires, and they used to be referred to as the tip and the ring. I suspect that's got something to do with the fact there was a form of jack plug often fitted to phones that you could plug in. So you've got tip and ring, and you've got a bell, which is a ringing device, and a capacitor in series with it. Now that was essentially the circuit when the telephone receiver was in place, and the telephone was, if you like, on standby waiting for a call. And the reason for the capacitor will hopefully become obvious in a moment, because if you take a multimeter and put it on the tip line and the ring line, this is the answer you get. This is the answer I got yesterday when I did it. On my line, which is at least 600 or 700 meters from the nearest box, there's 52 volts on my line DC, which is quite a lot really, and obviously that 52 volts would make a very good job of ringing that bell, but as we all know, a capacitor effectively treats DC like it's open circuit. So the DC does get used to run various circuits in the phone, but that only occurs once you've lifted the receiver. So when the exchange or the public switch telephone network, as it gets called in the UK, wants to ring you, there's an AC voltage applied to that line, and obviously the AC voltage is able to bypass that cap that's in series with the bell and causes the ringing sound to occur. So that's what we're dealing with. And obviously, as certainly the phone I had in my property as a child was had a real live bell on it that actually rang. It was an electromechanical device. So this chip is actually a replacement for the bell, and it's quite an interesting circuit. So let's just take a look now at the chip that I recovered, and it was the UTC31002, and it's, as you can see, it's a dual inline package, and I managed to get it out in reasonably good condition. And looking at the data sheet, what we've essentially got is a bit of power supply circuitry, and then you've got two oscillators, the low and the high oscillator, followed by an amplifier, and that sort of doesn't look particularly remarkable until you actually start looking at the application circuit. So again, from the data sheet, here's the application circuit, and it's quite interesting. First thing to note at a glance is that circuit has no conventional power supply. It obtains all its power from the telephone line. There is no external power supply. And so the way it works, pretty straightforward really. And if you look on the left hand side there by the tip, we've got a 0.9 microfarad capacitor. Interesting value. Certainly haven't got one of them in my box. 0.9 microfarad capacitor, which is effectively doing the same thing as that series capacitor was on the bell circuit of the older style phones, and that's blocking the 52 odd volts of DC from getting any further, which is a good thing, as you'll see in a minute. So next thing you've got after that load resistor there, you've got a bridge rectifier, and the bridge rectifier essentially takes the tip and ring supply from top and bottom and produces the negative going voltage on the left and the positive going voltage on the right. You've got capacitor C4 there, which effectively is a smoothing capacitor, and there'll be obviously voltage drop across the 560 ohm resistor and across the diodes, so certainly they seem happy that 35 volts is okay. I might want to go a little bit higher than that with 52 odd volts on my line, but it's probably alright. And then you've got a Zener diode, a 29 volt Zener diode. Now in recreating this circuit, I don't have a 29 volt Zener, which is probably not surprising, as I suppose too many people do these days. However, the reason that's there is because, if you refer to the datasheet, the maximum voltage allowable on pin 1, which is effectively the power supply incidentally is positive on pin 1 and the negative on pin 5 at the bottom right. But maximum voltage is 30 volts, so that Zener will crudely regulate the voltage so it doesn't get above 30 volts and protects the chip. And then you've got various other bits of circuitry. So just quickly looking at pins 3 and 4, you've got R2 and C2, and they between them regulate the low frequency sound of the bell. And then you've got on pins 7 and 6, yeah, that's right. On pins or 6 and 7 if you like, you've got C3 and R3, and those two regulate the frequency of the higher note of the ring. Now the 5.6 to 1 megohm resistor, which is attached to pin 2, is actually to do with the threshold at which this chip actually initiates a ring. And one of the reasons that's there, according to the datasheet, is to allow you to attach it to lines which you've got are a long way from the exchange and have got a lower voltage available when the ringing occurs. So that's essentially to allow you to adjust the point at which this thing triggers. Beyond that, you've got out of pin 8, you've got the output. There's a DC blocking capacitor there, C5, a 10k pot, which is a volume control, and then you've got a transformer and a speaker and a 15k resistor across the transformer. The reason for the transformer is this chip's capable of driving piezo transducer directly, which would have a much higher impedance than an 8 ohm speaker would. And in recreating the circuit, the bits that I couldn't really put in were the 29 volt Zener, and I've just used a transformer that I've actually got available. It's not a 1300 to 8.1, but it works. So yeah, an interesting circuit, and I think just as a reminder, that is completely dormant normally most of the time. It's only when the AC ringing signal is able to cross C1 on the left that voltage appears either side of the bridge rectifier and causes the chip to come to life. So it really is an electronic bell, and it's quite a complicated bit of circuitry compared to an electromechanical bell, and I suppose these things are going to become ancient history fairly soon, as the projected switch off of the old style analog phone system here in the UK is going to be completely gone by 2025. I know some countries have already achieved that, so this really is going to be ancient history. Right, let's now go and have a look on the bench at this circuit that I've attempted to recreate on the breadboard. Okay, here's my attempt to simulate the circuit on the breadboard. So we've got the DC blocking capacitor here. Now this is actually a capacitor I removed from the phone, and at the same time as I removed the chip, and I didn't realise at the time this is probably the actual DC blocking capacitor that was in circuit with the phone. It's 1 microfarad non-polarised. So there's your DC blocking capacitor. I haven't included the 560 ohm dropper resistor because I'm not going to be feeding a voltage in that's any higher than about 29 volts, so that's no problem. There's your bridge rectifier just there. Here's your smoothing capacitor. Again, no 29 volt Zener, A, because I haven't got one, B, because it's not required. I'm not going to exceed that voltage. And then we've got this resistor is the resistor that controls the threshold at which it starts to ring. You've got capacitor and resistor here and here, which are the low and high frequency controls, and this is the DC blocking capacitor from the output on pin 8. Transformer obviously, and I've got this just attached to my bench speaker. Now to set it up, I just used a DC power supply, so let's just have a look at what goes on, and to do that we'll just take a couple of voltage measurements. So I've got a voltage on the power supply at the moment which is about just under 29 volts, something like that, 29 volts DC. And as I say, I'm just trying this out, so what I'm going to do is bypass the blocking capacitor, because if you look beyond that into the circuit itself, there isn't any voltage because that's effectively blocking the DC. So I'm just going to bypass that capacitor, and you're hopefully going to hear something that sounds suspiciously like a phone ringing. There we go. So that's just nudged the capacitor there. Let's just do that again for you. So if I apply the voltage bypassing the capacitor, the circuit is triggered, So we should have, let's just double check, we've got a voltage going in at 28.7. Beyond the bridge rectifier, that voltage is 28, so that's the forward voltage drop of the diode. I'm going to turn it off so you don't have to listen to the noise, but essentially that's just working away there with a steady DC voltage. Here's a grab of the screen of the output, so those are the two frequencies. You can see the two different tones there, and if you put the cursors on each of those separately, you get the two different frequencies here and also here. And the ripple on the power supply looks something like this, so it's relatively minimal. So I think that's probably quite a reasonable interpretation of a telephone. In fact, if I do that, sounds suspiciously like one of those electronic telephones that were popular in the 80s and 90s and 00s, and still plenty about today. So that's working on DC voltage. I'm just going to get set up on AC voltage and then I'll come back. Okay, so now I've got the circuit reconfigured. I've got the speaker unplugged momentarily just so you don't get driven daft by the sound it's producing. So these two blue wires are now the incoming supply, which is AC. So let's just convince ourselves of that. Yeah, it's saying about 23.3 volts AC. The great thing about the Kaiweets in auto mode is it'll just flick between AC and DC without me having to change it, which is actually very handy when you need both hands. So 23.25 volts coming in, and then across the smoothing capacitor, bearing in mind the chip is running about 22 volts under load. And if you put the scope there, you can see there's the ripple, and you probably would want, might be slightly better if there was a Zener diode in there and the supply voltage was higher, but we're not too concerned about the quality of supply. It's just a telephone ringer, and I don't think people are listening too much to the audio when they're working towards the phone to try and answer it. So let's plug the speaker in. There we go. So first thing to note is that sounds somewhat different when obviously we've got AC supply going on. So we've got a different, we've got that ripple on the power supply, and we've also got a slightly different voltage. So what we would need to do to get that to sound like a phone is to tweak that capacitor and resistor, and to tweak those two as well. That's a very, I'm going to just stop that. That's very tedious, and I'm sure you'd be bored to death watching me do it, so I'm not going to bother, but you get the general gist. In fact, the datasheet contains the formulae to allow you to calculate those two numbers. So that's me recreated the circuit, and this is probably something that once we've got rid of the public switch telephone network, there's no longer a requirement for these. I don't know whether you can still get them, I haven't even looked, but that's an electronic bell, and these things were, or some similar make, were pretty much in every desktop telephone that didn't have a bell. So there's probably been millions of these produced over the years, and it's a bit of a random circuit that I'd never heard of before. Okay, well there you go. Appreciate the subject probably wasn't for everyone, but if I'm honest, I've really enjoyed researching what this chip actually did, and certainly researching how the telephone system was set up and worked for many years, and amazing that even today it's still capable of supporting that old technology, albeit for not very much longer. So I hope you found it interesting. There's some really good resources out there on the internet. In particular, there's a resource to do with the circuits of some circuit diagrams of the old telephone systems here in the UK. It's the old post office telephones repository, so I'll put a link to that in the description, and if you're interested, there's some interesting things to look into there. If you're of a certain age, you may remember a few of them. Thanks very much for watching. It'd be great if you could like the video, that really helps, and even better if you could subscribe as well. There are some links in the description to the Kaiweets tools website. If you have a look there and there's anything you fancy, if you buy it and use the code that's also in the description, that'll help the channel. I'd appreciate that, and see you on the next video.